Okay, sixth graders, here we go. This is, as you can see, a slideshow. We're going to be learning about the atmosphere. This is assignment number 27. So on your paper, number it 27 and title it The Atmosphere. Okay, atmosphere. Okay, there we go. That's the title of it. And I like this picture here a lot. This is taken from the International Space Station, and it kind of shows you the thin, really, this little blanket of air we have. It's pretty amazing. It's we. One thing I think is important to keep in mind too is how did it get here? Now, when the Earth first formed, all the material was sort of coming together, asteroids and pieces of junk and floating in space and rocks colliding and stuff and accumulating. Gravity was pulling it all together. Now, at first it was liquid because of the heat of the impact would have had everything be molten. But remember when we learned about density, that the heaviest stuff, the densest material is going to sink to the bottom, right? Well, the same thing happens on the planet Earth. And so all the iron, the heavy metals would have sunk down to the bottom, and that is the center of the Earth. That is the middle. That's the bottom. That's downward, right? And the lighter stuff would have risen up to the surface. And so there's different layers of the Earth, with the liquid iron outer core, and then the mantle, which is made mostly of silica, which is like you can think of it as made of lava, essentially. And then you get the solid crust on the outside. Now, the lightest stuff of all is going to be water, and even lighter than water, less dense than water, is going to be air, okay? And so all the air and the water and stuff, as the Earth, as it cooled down and solidified and the lighter material rose to the surface, basically it would come busting out of the Earth's crust in these enormous volcanoes, way bigger than any kind of volcanoes we have nowadays, and all the water to fill the oceans. Then it would have rained down to fill the oceans, and carbon dioxide and helium and stuff like that, and hydrogen. A lot of that would have just floated away because it's not very heavy. But the nitrogen would have stayed on the Earth, and the carbon dioxide would have stayed on the surface. Again, it's all attracted by gravity. And as the heavier stuff sinks to the middle, the lightest stuff rises to the surface. And so an interesting thing now is there's a theory about how much of the Earth's water has actually come from comets and things like that from outer space. And, well, the answer is really all of it if you include the material that made up the Earth came from outer space too. We are in outer space, right? Well, anyway, this is a process called outgassing, and it would have been the early formation of the Earth, way before there's anything like life or anything of that sort, where just all the air and the oceans, basically, all the water would have come gurgling out to the surface and then accumulated on the surface. Really interesting period of Earth's history, or prehistory, I should say. Now, keep in mind, there wasn't any life or anything, which means there wasn't any free oxygen either. It didn't have any loose oxygen. You wouldn't have been able to breathe this original atmosphere. Okay, so anyway, we're going to go ahead and keep pressing forward here. Now, this graphic here is basically showing if this is the Earth, how much volume of water would there be? And that would be like that drop there. And that would have been distributed around the surface of the Earth in the oceanic basins. And so that with air, there's a little bit more. You can see that this pink ball is supposed to represent how much atmosphere there is, and it would be surrounding the Earth. Held to the Earth by gravity, being pulled. Yes, air has weight. Air is pulled by gravity. When we get to air pressure, that's really super important. And anyway, that's the gravity that holds the air to the Earth. Okay? Okay, and so here's, again, anything I write down, you need to write down, okay? Let's talk about what different kinds of gases are in the atmosphere. Now, way back in the olden days, you had guys like Aristotle and stuff that said that if there's basic elements, earth, air, fire, and water, and so people thought that air was basic element. Well, it wasn't. It turns out it's made of different kinds of gases, and we've already talked about oxygen and carbon dioxide and stuff like that. But what are the percentages? And do you remember from the reading? I had you guys draw like a pie chart on that. At any rate, the most common gas, what is it? Try to remember. Say it if you know. Here's a hint. Starts with an N. It's what? Nitrogen. So nitrogen is the most common gas in the atmosphere. Please write that down. Okay? Now, when we did with the atoms and stuff like that, basically what that becomes is like N2, where two nitrogens will stick together. And if you recall this, 1, 2, 3, there was a triple bond. Do you remember that? There was like a triple bond between nitrogen atoms to make a nitrogen molecule. Anyway, that's going to be important later on in the lesson, and it's kind of a significant thing. Now, what I really need you to know, though, is nitrogen is the most common gas. What percentage? Do you remember? What percentage? And if you said 78%, you are correct. Guaranteed test question. What's the most common gas in the atmosphere? Nitrogen. What's the percentage? 78. Guarantee it. Okay, the triple bond thing probably won't be a test question, but here we go. So now the second most common gas in the atmosphere, I think you guys all know this. Basically, a lot of people think that's what the air is made out of, but, well, it has it in there because it's really important because we die without it. And what is the gas called? That's right, it's oxygen. Nitrogen and oxygen. And then oxygen also will form O2, so it'll become a molecule where you have two oxygens together. Now, I don't know if you guys remember this again from when we did the chemistry and had the bonding of the atoms. That would be a double bond between oxygens. And what is the percentage of oxygen in the atmosphere? Do you remember from the lesson? It's 21%. 21%. Okay, so again, guaranteed test question. With nitrogen 78%, oxygen 21%. All right, now 78 plus 21. What's that? Let me see. 8 plus 1 is 9. 7 plus 2 is 9. 99%. Right. So that's 99% of the air. Every time you take a breath, 78% of the molecules that go in your lungs are nitrogen, 21% are oxygen, right? That's 99% of the air. But that's not the only thing there is. Now, we're going to ignore most of that other 1% because it's mostly argon, which, do you remember, it was an inert gas, right? It's way over in the noble gases, so it doesn't do anything, right? So argon, we can ignore argon. But there's another super important gas, which the book just kind of said, trace gas is 1%. But it left this one out, and I couldn't believe it because this one is super duper duper important. And that would be, what is it? If you said carbon dioxide, you're right. Carbon dioxide. Okay? And that is CO2, which is basically, remember, carbons always have 4 and oxygens have 2. That's kind of what the molecule looks like, where you have double bond between there. So you have 2 oxygens and 1 carbon, CO2, carbon dioxide. Now, here's the thing about carbon dioxide that is amazingly, I mean, to me, this is like, whoa. 99% of the air is these other ones. That means just less than 1% is carbon dioxide. In fact, way less than 1%. Because most people think carbon dioxide and oxygen are kind of equivalent. Well, 21%, that's a lot. That's a high percentage. Carbon dioxide is 0.04%. Okay? 0.04%. That's 400 parts per million. Okay? So think about how many parts a million is, and only 400 of them is carbon dioxide. This is a teeny little percentage, but it's really, really important. And I'll tell you, since I'm teaching about this right now, I'll just mention this. The fact that it's such a tiny little percent, that's not 4%, that's not 40%, that's not even 0.4%, it's 0.04. That's 4/100ths of a percent. That's 4/100ths of a 100th. It's 400 parts per million, right? So at any rate, this tiny little percentage is why human activity can affect the level of carbon dioxide in the atmosphere. It's because, tailpipe emissions and when people burn coal and stuff to generate power, you go, well, the atmosphere is huge. How could beings possibly affect it? Well, because carbon dioxide is a greenhouse gas. We'll be learning about that more. It's a fossil fuel emission, but it's because it's such a tiny little percent that it is possible to change that percentage. It's a tiny percent, but it's an important percent. When I first started teaching this, I taught my classes the same lesson, except the answer wasn't 0.04, it's 0.036%. That was what the answer was. And then it turned into 0.038%, and then now it's 0.04%. And in fact, it's probably going to be a little bit higher than that. Oops, I just did that wrong. 0.038%. Oops. At any rate, you see how easy it is to make that mistake? Don't make that mistake. 0.036%. 360 parts per million, 380 parts per million. I've watched, as I've taught earth science, I've watched the level of carbon dioxide increase. Okay, at any rate, this is carbon dioxide. Nitrogen, oxygen, carbon dioxide. I think we could make that into a song. What do you think? Nitrogen, oxygen, carbon dioxide. Oh, what fun it is to breathe our atmosphere tonight. Hey! Okay, so at any rate, that's going to be the ending verse of the Layers of the Atmosphere song. Okay, carbon dioxide. Now here's the thing I want you to remember. This is the second time we've come across this. There will be another coming across when we get to cells. Oxygen and carbon dioxide are super important for that thing called photosynthesis, right? For photosynthesis, remember that? You got CO2 plus H2O gives you glucose. Now, this isn't going to be, I don't know, maybe I'll put it on the test as an extra credit question. But I just want to remind you again, you can't learn something like this by seeing it once. You got to see it more than once. So here it is again. Glucose. You remember the formula for glucose? Yes, you do. That's very good. C6H12O6. Okay? And then plus oxygen as a waste, right? O2. Now, CO2 and H2O. Okay, we could make this a balanced equation by how many carbons you got there, so you need 6 CO2s. How many hydrogens you got? 12, so you need 6 H2Os. And that's going to give you 18 total oxygens coming out, so there's only 6, so you need 12 more, so that's going to be 6 O2s. Yeah. Okay, so anyway, write that down. This is photosynthesis. Okay? And what I want you to remember now is carbon dioxide. Look, you can't do photosynthesis without carbon dioxide. Oxygen, look, you can't, it ends up being a waste product. And remember, when you use the energy from your food, it reverses that for cellular respiration. So you need to have that oxygen to release the energy that's stored in the glucose. Okay, so anyway, we talked about that before. There it is again. So